Okay, now getting on to electromagnetic induction. So, what we need to know for electromagnetic induction is all of the terms listed involving flux, electromotive force and induction, and Faraday's and Lenz's law. And then we need to solve problems involving these terms and laws. So, electromagnetic induction is the production of an electromotive force, causing electrons that are free to move to migrate to one end. As a result of this movement of electrons, a potential difference is going to be caused, or in other words, a voltage. So, as you can see, in this case, the magnet moving is going to produce a force in this coil, which is going to create a current, which we have measured with this galvanometer. So, the strength of the EMF induced depends on the rate of change of flux linkage. For the movement of wire through the field, EMF is given by the magnetic field strength multiplied by the length of the wire multiplied by the velocity that the wire is traveling at. If the wire itself is not perpendicular to the field, then we need to consider the angle at which the wire is at with the field. And this is, of course, because as the wire becomes more and more parallel to the field, it's going to be experiencing less and less of the force. So if this is our field, and then we'll have our wire. If the wire is perpendicular to the field, then like every single point of that field is going to be like interrupting the wire, right? However, if the wire is kind of at a diagonal, then some of the field or some of the field's components are going to be missed because this wire now has components that are in the same direction as the field, meaning that they're not experiencing anything. Of course, if a wire is just like this and it's parallel with the field, then none of the lines are intercepting with it. So that's why we need to consider this sine theta. What this tells us then is that if a wire is completely parallel to a field, or in other words, if theta is 0, then there's not going to be any force induced. And that's of course because the sine of theta of 0, is equal to 0. So that's just something to remember, mostly for kind of maybe a multiple choice question. So now getting on to Lenz's law. So Lenz's law is kind of, at least what I considered in year 12 to be the most difficult part of electromagnetism. So Lenz's law is an expression of negative feedback. What this means is that the current induced in a conductor by a changing magnetic field is in such a direction that its own induced magnetic field opposes the change that produced it. And this is kind of hard to wrap your head around. So, what this basically means is that if you induce a current using a magnetic field, then the current you induce is going to kind of like retaliate, and it's going to generate its own magnetic field in a direction that opposes your own magnetic field, right? How I kind of thought about this in year 12, just because it was kind of such a difficult concept for me, I had to think about it a lot, was that the current that I was inducing was like being a little bit petty. You know what I mean? Like, and there is actually a scientific explanation for this, which I'll get into in a second. But how I kind of thought about it was the current was being petty. Like, I was trying to generate this current using my own magnetic field, and then the current that I was generating or inducing was kind of being like, I refuse this. I refuse this magnetic field that you're introducing. It was kind of being petty. Now, the actual reason this happened is obviously not because the current is being petty. It's actually due to the law of conservation of energy. So, I'll explain this in the context of, I don't know what that word was, in the context of the solenoid, which we have here. So, here we have our solenoid, and as you can see, the magnet is moving in. When the magnet is moving into the solenoid, the current is going to be induced to oppose that motion, right? So basically, you're trying to move the magnet in, and as a result of this changing magnetic field, remember, a changing magnetic field generates EMF. A changing magnetic field induces our current. You are changing the magnetic field by moving this magnet, and as a result, the current is kind of refusing that, and it's generating its own magnetic field to oppose that. And as a result, it's going to generate a current with north in this direction so that it opposes your magnet. Now, the reason that this occurs, as I said before, is the law of conservation of energy. So think about this. If you moved your magnet into the solenoid and it induced a current that pulled your magnet in. So you're standing there next to the solenoid, you have your magnet, and your solenoid is like pulling the magnet in, right? This doesn't make sense. Think about why this scenario doesn't make sense. Pause the lecture for a second and have a think about it. It doesn't make sense because that energy has just been like newly created, right? There is being a current that's induced, and your magnet is being pulled in. There's no resistance you're facing. It doesn't make sense. What does make sense is if you are changing the magnetic field, there needs to be an opposition to that motion to generate energy to create the current. So if you're pushing the magnet in and you have to it's being opposed, so you have to push in really hard. You're putting all of this energy into pushing the magnet in, and all of that energy that you're putting in, your applied force, is giving the electrons the energy to move around the solenoid. So the reason that Lenz's law occurs is because of the law of conservation of energy, right? You need to put energy into generating that current. This again occurs in the other scenario where you're moving the magnet out of the coil. So imagine you have your magnet in the coil and now you're trying to pull it out. But the coil is like pulling it, trying to keep it in the center. So you're trying to pull it out, the coil is trying to keep it in the center. The reason for that is because you are changing the magnetic field, which is going to induce a current, and you are inducing a current around the coil. So if you didn't need to pull on the magnet and put energy into pulling the magnet, there wouldn't be any energy for the current to be induced. So, of course, you're pulling it out, which means that the current is going to generate a magnetic field strength that opposes that motion. Again, the current is being petty. It's saying, oh, you want to move that magnet? I don't think so. I'm going to create my own magnetic field that stops you from doing that. That's how I still think about it to this day. So because of that, the direction of the current between these two images is going to change because now it wants to keep the magnet in there. So now this end is going to be the south because the direction of the current has changed. And it's going to pull the magnet back in. Okay, so that is basically the overview of Lenz's law and how it applies. This law kind of, as I said, was really tricky for me to understand when I was in year 12, especially when you get into like the application questions, and you need to apply Lenz's law to a whole different number of scenarios. So yeah, I hope that explanation really helped because it took me literally months to fully understand that. I'm not gonna lie to you guys. So by considering both Faraday's law and Lenz's law, we can derive an equation for the EMF induced in a loop with changing flux. So remember, the EMF is induced because the flux changes, the magnetic field changes. The section here about the EMF being proportional to the change in flux over the change in time is of course from Faraday's law, and then the negative out the front is of course from Lenz's law because Lenz's law tells us the direction of induced EMF and Faraday's law tells us about the magnitude of the induced EMF. Okay, getting on to mutual induction and transformers. So this topic is pretty simple. We'll go over it kind of quickly. So a pulsing, alternating magnetic field can be induced by feeding a coil with an AC current. So this magnetic field will induce a current of the same frequency in adjacent coils. And as a result of this, if the number of coils differs, the voltage can be stepped up or down according to this formula. So recall the use of transformers is, of course, if you are transporting electricity across long distances, such as in power lines in rural areas, you need to have a high voltage because that will reduce the power loss. However, when you're actually using power or electricity in your home, you don't want that larger voltage. You only have like regular appliances. So what you want to do is you want to change the voltage. And how we do that is using our step up, step down method with our two coils. So if you have energy moving in this wire and then it is put through this coil here, and then if you have another coil here that has less turns, what's going to happen is the energy is going to travel along here, and then it is going to go through this coil here, and the movement of the charge through the coil is going to generate a magnetic field, which is thus going to impact this coil, generating a charge through this coil, which will then move off in this direction. So that's why that works. And of course, our voltage of our primary coil divided by the voltage of our secondary coil is going to be equal to the same ratio for the number of turns. So if the number of turns is different, that means that we can determine or change, or step up or step down the voltage. We can do the same thing with the power. So we know that the power of the input and the power of the output always needs to be the same, because if it weren't, then we would have lost or generated energy, which doesn't adhere to the law of conservation of energy. Remember, power is given by VI, so that's why this equation exists. So the power in the primary coil is going to be equal to the power in the secondary coil. Okay, before we move on to special relativity, I just want to give you guys like a few really quick tips for studying electromagnetism. One thing I really, really, really want to emphasize is making sure that you practice complex questions for especially like electrostatics and electromagnetism, like with like magnetic fields and the current carrying wires and moving point particles and solenoids. And the reason for this is because there's always going to be a really complex question of these on an exam. And you really need to understand the interaction of multiple different components. So for electrostatics, you're going to need to understand the interaction of 3 or 4 particles and how they impact one another, how their electric fields impact one another. You're going to need to do like vector analysis involving trig. So make sure that you practice those. And then for your electromagnetism, make sure that you practice questions that involve a lot of different elements. So that could be a current carrying wire, a moving point particle, a solenoid. Make sure that it includes Lenz's law, Faraday's law, all that kind of stuff. Make sure that it involves the right hand rule, this rule here, the FBI rule. Make sure that you practice combining all of the components together. Because speaking from experience, the reason that I lost marks on my physics external was because I didn't get one of the difficult magnetism question. I think I only got half marks. So yes, that is what really bugs me. And I practiced a lot of these questions. So that's my tips. Okay,